Right, so we are told that we have two beakers, A and B, containing base. Beaker A is a 500 centimeter cube of barium hydroxide of unknown concentration. And then beaker B is a 400 centimeter cube potassium hydroxide solution. Okay, so the basics for now are that we have two solutions, two different solutions. We've got beaker A and beaker B. Beaker A is 500 centimeters, and it is barium hydroxide, and we don't know the concentration. Then in beaker B, we've got 400 centimeters cubed of potassium hydroxide of concentration 0.1 mole per decimeter. Okay, that's what we know so far. Question 7.1, define a base according to Arrhenius. Okay, so this isn't that important, but Arrhenius was the dude or girl. We don't actually know if it was a boy or a girl. Got to be careful these days. So we don't know. It says define a base according to the Arrhenius theory. And so a base is something, so we'll say a substance, which produces hydroxide ion, so OH minus in water. Okay, that's what Arrhenius defined a base as. If you're saying, no, Kevin, it's not quite right there, buddy. It's actually that a base is a proton acceptor. That's the Bronsted definition. Okay. Question 7.2, calculate the number of moles of hydroxide ion in beaker B. So if you take a base, now examples of bases would be sodium hydroxide, potassium hydroxide, barium hydroxide. These are some examples of bases. When you put bases in water, they don't ionize, they dissociate, except for ammonia, but that's just an exception to the rule. So normally what bases do is they dissociate. So if we look at beaker B, that's potassium hydroxide. Now, if it dissociates, it means that it breaks up into its ions like that. Okay. Now, we need to remember all the valencies and things like that. So we know that potassium is +1, and we should remember that hydroxide is -1. Okay. And so the reason I'm doing this, guys, is that you can realize that this equation is already balanced. So what that tells us now is that the mole ratio of potassium hydroxide is 1:1 with potassium and also 1:1 with hydroxide. It won't always be like that. So it's very important that you look out for that first. So, so if we take this information over here and this over here, that is the information for the potassium hydroxide, which is this one over here. So we can take that concentration and that volume, and we can work out the moles of potassium hydroxide using this formula over here. And so we can say 0.1 is the concentration. The number of moles, we don't know. And the volume is 0.4. Remember that this must not be in centimeters cubed, but rather in decimeter cubed. Okay. And so then what we can go and do is work out the number of moles, and that's going to give us 0.04. But now this is the part where many learners could make a mistake. What we must look at now is that this is the moles of potassium hydroxide. Okay. Now, if you look at the ratio of potassium hydroxide to hydroxide is 1:1, but it might not always be like that. Okay, it's 1:1. So that means that if the moles of potassium hydroxide is 0.04, then it also means that the moles of hydroxide is also going to be 0.04. So we can say, therefore, the moles of hydroxide will be equal to 0.04. But sometimes there will maybe be a 2 over here or a 3. Then you got to be careful. Okay. If we look at some acids, some examples of acids would be HCl, H2SO4, and HNO3. Some examples of bases would be potassium hydroxide, sodium hydroxide, and barium hydroxide, for example. Okay, and then I'm also going to give you the exception, which is ammonia. Right. Now, what we know is that acids, what they do is they ionize. They ionize. So what does that actually mean? It means that they react with water. They react with the water. Okay. So what does that mean? It means that they react with water. So if we look at HCl, if it reacts with water, then it becomes Cl minus plus H3O plus. Okay. Now H2SO4 is diprotic. Diprotic. What does that mean? It means that it gives away 2 protons. So what that means is that it's going to react with the water, and then you're going to end up with SO4 minus 2 plus H3O like that. And if you had to go balance this, I'm just going to go through it quickly now, but if you had to balance this, you should put a 2 in the front here and a 2 over there. So there is another example where the balancing becomes very, very, very important. Otherwise, you are always going to assume that everything is just 1-to-1 the whole time. Okay, then HNO3, nitric acid, also reacts with water to become H3O plus NO3 minus. Now we're going to move on to the bases. Now bases, they are totally different. They don't ionize. What bases do is that they rather, they rather dissociate. They rather dissociate. So for example, what that means is that they don't react with the water. They don't react with water. They just break up. They break up. And so it looks like this. You see that, guys? They are breaking up. They're not reacting with the water. They're actually just breaking apart. That is what dissociation means. Now, let me just show you NaOH. See how it just breaks up? There we go. Now, some people get a bit confused with this 2 over here. What I tell them is don't worry about the 2. Just put the barium and the hydroxide like you normally would. Now, barium, if you look on your periodic table, has a valency of +2. Now, if I do balancing, I should realize eventually that there needs to be a 2 in the front over there. Then it's balanced. You see, guys, so when barium hydroxide dissociates, the ratio between the barium hydroxide and the OH is a 1-to-2 ratio. It's not always 1-to-1. It's important that we see that. And then we've got good old NH3. I don't know why NH3 had to be different, but it's different. NH3 is a base, but it ionizes. So remember what ionizes means? Whoops, why do I keep doing that? It means it reacts with the water. So we're actually going to say plus H2O over here. See how we say plus H2O? Whereas with these bases, we didn't do that. The product of that would be NH4. It's not going to get, this NH3 is not going to give its proton away. It's still a base. It's just reacting with water. So it's going to get a proton from the water molecule, and then you're going to be left with OH minus. Right. So this is where we were earlier. So here we go. Here is the question that I've got a feeling caused a bit of a tornado for some students. I've had a lot of students tell me that they want me to include this one, and it just looks scary. Like, I can imagine being a student getting to this question, and I can imagine that it would cause a bit of a panic attack. First of all, this just looks, this part here just looks scary. Second of all, 8 marks. I mean, come on, that's enough to have a heart attack. But I'm going to show you guys that this question, it's good, but I'll try and make it as easy as possible for you guys. What we have is, in question 7.2, they gave us this container here, which has barium hydroxide, and then they gave us this potassium hydroxide. What we're going to quickly do is we're just going to go pour all of that into one container. That's all we're doing for now. We're just going to pour that into one big container. So let's draw a big container for ourselves. And this is called container C. And this container is going to have a mixture now of A and B. Okay, so maybe we can remember that we put a bit of A in here, and then we put a bit of B in here. Okay. So we throw everything together, we mix it up, and now it's just one big mixture. So what would the volume be? Well, of course, the way that liquids work is that when you throw them together, their volumes add, okay? This part here where they said that the volumes are additive, that was just there to, that wasn't really necessary. It's only when you start doing like PhD chemistry type stuff where sometimes when you add 2 liquids together, the volume doesn't add. It goes up a little bit less or whatever. But that's because there's a big chemical reaction happening. So of course, if you put a 500 and a 400 together, then we're going to have a total of 900. Okay, that is the solution volume. By the way, we do not know what the concentration is. Think about it. Let's say here you've got some Oros, and this Oros is very, very sweet. And then you put this Oros, which is very weak. If you throw them together, we won't know what the concentration is. Okay, so we can't say that the concentration will be 0.1. So we have no idea what the concentration will be. What we do know, though, is that the pH of this solution is 13. We know that for sure. So I think that's where I would start. I would go to my pH formula. Which is this, and I would fill in my pH. Now, the base of a log, if there's no number there, is a 10. All right, so what I need to do now is put the negative, I'm going to put the negative over here, so that's negative 13. And then don't panic. All we do now is we say that the concentration of H3O plus is going to be equal to 10 to the power of negative 13. Okay, so that's a good thing. We now know that the concentration of H3O plus is 10 to the minus 13. Now, what we can do, guys, what I realize in this question is there's a lot of OH. There's a lot of OH. So can we agree that there's probably a lot of OH floating around in this container? Because think about what we learned about earlier. We know that the barium hydroxide, it breaks up into barium and 2 hydroxides. And we know that the potassium hydroxide breaks up into potassium plus hydroxide. So we can be very sure that there is a lot of OH minuses floating around here. Okay. Guys, what we can now do is we can now use the KW formula. Like that, because we know that that is always equal to 10 to the negative 14. That is a formula that is given to you on your formula sheet. The reason I'm doing that is I know what this one is, this one here. That's the one we've just calculated. So then I can manipulate this formula and I can find the concentration of OH minus. Once I have the concentration of OH minus, then I can start. See, now it's more applicable to my system. Kw stands for the equilibrium constant of water. It's almost like Kc, which stands for equilibrium constant, but when it's Kw, it's just the equilibrium constant of water. Okay. Now, I can use that formula, as I said, so I can say 10 to the negative 13 multiplied by the OH minus is equal to 10 to the negative 14. And so if I now have to go work that out, I can say 10 to the negative 14 divided by 10 to the negative 13, and that gives 0.1. 0.1. So guys, what that now means is that I know the concentration of OH minus in this solution, right? I know that the concentration of OH minus is 0.1. And that should be mole per decimeter, of course. So we now know the concentration of the OH minus. We have the concentration of the OH minus in this solution. So I'm going to erase a lot of the stuff here because it's not necessary. Now, here's where the magic happens, guys. I am going to now take this volume and this concentration, and what I'll be able to do with that is I can work out the mole of OH minus in this container just using C equals to N over V. By the way, a lot of you are saying that you don't use this ugly formula. You rather use this one. It goes something like this. And I think I'm going to start using that from now on because I've had a lot of people comment on my videos before saying that that's the one they use. And I think it is actually quite a nice formula. So you don't always have to use Kw, okay? So now we know the concentration of the OH minus is 0.1. The number of moles of OH minus, we don't know. And the volume is 0.9, 0.9. Okay, now to work out the moles of OH minus in that container, we're just going to say 0.1 multiplied by 0.9, and that would give us 0.09 moles. Now, think about this, guys. We now know how many molecules or how many moles, sorry, the moles of OH. We know how many moles we have of that. Now, that tells us like, when you look at the moles, it's sort of telling you how many particles do we have in the container. So we know that we have 0.09 moles of OH minus. Now, where did that OH minus come from? Some of it came from here, and some of it came from here, right? Now, if you remember correctly, in the previous question, they asked us to calculate the number of moles of hydroxide ion in beaker B, and we calculated that as 0.04. So we know that this container over here was responsible for 0.04 moles of OH minus. So then we then poured this one and this one, we poured them together, and the total OH minus moles is 0.09. So what we can then do is we can now work out the moles of OH minus in this container over here. So we can say the number of moles of OH minus in beaker A would be equal to 0.09 minus 0.04. And that gives 0.05. That's not the answer. That's concentration. Okay, and that's how many moles of OH minus we have in this container. Okay, and so this is the moles of OH minus equals 0.05. So that's not the answer yet, guys. So now we know how many moles there are inside here. But the original question is asking us, calculate the concentration of the barium hydroxide. So they want to know what is the original concentration of the barium hydroxide. Now look at this, guys. We know that the barium hydroxide in that container reacted like this. So what we've just done now is we have now calculated the number of moles of OH minus in that container. So we can say that the moles of barium hydroxide to the number of moles of OH minus, the ratio is 1 to 2. So how many moles of hydroxide do we have? 0.05. And so if I want to work out this one over here, I'm going to have to divide the 0.05 by 2. And that'll be 0.025. 0.025. So now I know the number of moles of barium hydroxide in this container. And so now I can work out the concentration of the barium hydroxide by using this formula. And so the number of moles is 0.025 and the volume is 0.5. And so if we had to go work this all out, we get 0.05 mole per decimeter. Now, I do not expect that every person watching this right now understood that completely. That is almost impossible to understand that in one go. So what you guys need to do is you need to go and re-watch this question as many times as you need to, but don't just watch the question, pause the video and try it yourself and see how far you can actually get in the question. Okay. And do it 2 or 3 times, see how far you can get and make sure that you understand this one. Okay. It's not easy. But yeah, it's a good question. We are told that the solution in beaker C. Okay. So let's just quickly remind ourselves about beaker C. Beaker C was a 900 centimeter solution with a pH of 13 and a OH minus concentration of, jeepers, I have completely forgotten. And the OH minus concentration, just in case we need that, I'm not sure, was 0.1. Okay. We are told that the solution in beaker C is titrated, guys, titrated, very easy stuff, with ethanoic acid. It was found that 15 centimeters of the solution, okay, so we're not going to use all of this. Be careful. We're not going to use all of that. We're only going to use 15 centimeters of that one. So they're just going to pour a little bit. It says 15 centimeters of that solution neutralizes 30 centimeters of the acid. Okay, here we go. Let's see. So I'm going to write down, let me start with 7.3.2. Is ethanoic acid a weak or a strong acid? Give a reason for your answer. It is weak. Now, some of you always want to look at this and you think, why is it weak? Why is it weak? Guys, the only reason that I know it's weak is because that's a definition, not a definition, but it's part of the theory that we need to know. Okay. Ethanoic acid is weak. Now, what's the reason that something is weak? Is that it does not ionize completely. Okay, there we go. So what we're going to do is we're going to take this reaction and all we need to do is the following. Let's look at the ethanoic acid. What do we know? Let me show you how easy titrations are. What do we know about that ethanoic acid? Well, it's got a volume of 30 centimeter cubed. And we're trying to calculate its concentration. So we don't know what that is. If I look at the OH minus, I already know its concentration is 0.1. Yeah, but Kevin, we're not using all of it. So how can the concentration be 0.1? Guys, remember that concentration doesn't always change. For example, if this is a big container filled with OROS, let's say OROS, if that's filled with OROS, and then there's a little tap over here, and you pour yourself a little bit into a glass, wouldn't you agree with me that the OROS in the container and the OROS in your little glass is going to taste exactly the same? It doesn't become stronger. It doesn't become sweeter, sorry, or more sour or more dilute or anything like that. It's going to taste the same. So concentration is not going to change in this question. And then the volume is 15. And that is all that we need. The way a titration works is they'll give you these two pieces of information and they'll give you the volume, for example. So what you do now is you combine these two to give you the moles, just using this formula over here. And so the concentration would be 0.1. The number of moles we don't know. And the volume is 0,015. Remember, it must always be in decimeters. And so if we had to work out the number of moles of the OH minus, we would get 1.5 times 10 to the minus 3. Then what I do is I look at this reaction that's taking place. And I look at the ratio between the OH minus and the CH3. And I see that that ratio is 1 to 1. Okay, it's a 1-to-1 ratio. And so that means that the moles of CH3COOH is also going to be this amount over here. So we can say, therefore, well, let me first make it nice and clear for you guys. So we can now say that the moles of CH3COOH to the number of moles of OH minus is in a 1-to-1 ratio. And so if we have 1.5 times 10 to the minus 3 here, then that means this one must also be 1.5 times 10 to the minus 3. So now all of a sudden, I have the moles of ethanoic acid. And so then I can combine these two now to give me the concentration by using this formula over here. And so that's going to be 1.5 times 10 to the minus 3 over the volume, which is 0.03. Remember, it must always be in decimeters. And so if we go calculate that now, we get 0,05 mole per decimeter.